I didn't expect this big screen, so but you're definitely gonna see everything. So hello everyone, my name is Adam, and to just start off, like you see, I'm gonna talk a little bit about gRPC and HTTP2, and just a little story of how we use OCaml at Dialo. But just to start, like, who here knows what gRPC is or uses gRPC? Okay, nice. That's good. That's super good. And who knows what HTTP2 is and knows more or less how it works? Okay, that's good. I have a crash course for HTTP2. I'm prepared. So let's just begin. We have a lot to talk about, like I said. Wow, that's a big face of mine. Like I said, my name is Adam. I'm a software engineer at Dialo, and which is a company placed here in Warsaw, and we use OCaml there quite extensively. And we are a very small team, so I do a lot of stuff there, but mostly I do like systems engineering on OCaml, and my work was and is especially focused around implementing and maintaining several network protocols which we just write from scratch in OCaml. So to begin with, why we do even implement those protocols that I'm going to be talking about today. In the first place, let me just introduce you of what we do and where is OCaml used in our stack and how the infrastructure works, where are those protocols used. So we are a company that creates like voice AI for the telephony network. We work mostly for banks and other financial firms. So for example, when you want to lock your card or unlock your card and you call your bank in Warsaw, you're talking to our bot, you're talking to OCaml. And we do a lot of stuff in OCaml to achieve that. The AI itself is not in OCaml, but we do a lot of stuff in OCaml. So just to give you the high level view of what that looks like and where are those protocols, well, this is the very high level perspective of the infrastructure. We have some mobile telephone provider, network provider like T-Mobile. Then we got some our internal SIP telephony server, and we're talking about communication protocols here. So those are connected with gRPC and RTP, and those are also implemented in OCaml. But we're not going to talk about them. But just for the context, SIP is like a transactional protocol for exchanging metadata in a telephone call, and RTP is like the most basic protocol on earth for real-time audio. And those goes to some internal services where all of the AI happens, and these are connected with gRPC, which I'm going to talk about today. And what's important here is we handle like even up to hundreds of thousands of calls daily, and which means hundreds of calls, concurrent calls, which means even more hundreds of concurrent gRPC connections. And the second thing is this was actually, for the most part, a single process. So what I'm trying to say is you had to have like a decent implementation of those protocols to handle this many real audio traffic, like a concurrent real audio traffic. And the reason that we were implementing HTTP2 and gRPC in the first place was a very slight problem. This is the problem. And unfortunately, our metrics don't last that long. This is supposed to be a screenshot, but that will do. And so how do you fix a memory leak these days? You just restart the service, right? And you do this 3 times a day, and problem is solved. And I'm kidding, obviously, but this is apparently like an industry standard that you just restart the service instead of fixing memory leaks, which kind of surprised me when I first find out. So long story short, after long digging of memory, it was the memory leak bug was in the HTTP2 implementation, which for those who don't know, HTTP2 is like a transport protocol for gRPC. gRPC uses HTTP2 for streaming data, which kind of surprised me because this is a like pretty decent implementation, which is used all over the place in OCaml ecosystem. I actually was really looking forward to meet Antonio, which is the creator of this implementation. Unfortunately, he's not here. So I was pretty surprised, but my best bet is like this implementation is like implemented to, well, HTTP2 is created mostly to serve websites to browsers. So it was created for like a request-based performance. And in gRPC, we need more like a database performance for streaming. So we did end up implementing our own HTTP2. I did end up implementing. But this is not the first path you're gonna go when you have a bug in this implementation. So let's first go, why didn't we just patch this implementation in the first place? And there were a couple of reasons. First of all, this was based on the older RFC, not the latest specification. And actually the bug that was, from my investigation, the bug that was causing the memory leak was in the logic that should be removed anyway, according to the latest specification of HTTP2. And well, this logic that should be removed anyway was so tightly connected to every other piece of code in this implementation that it basically was just easier to re-implement the whole thing and be compliant to the latest spec. And actually, this implementation is also modular to several asynchronous backends, which also adds some complexity. But this also might be my skill issue as well. But I really try to fix it. This is also an opportunity for us to experiment with effects. Everything we do in OCaml, we do with AO right now, which is like an effect-based scheduler. So this was kind of opportunity for that. And we wanted to re-implement gRPC anyway because it had several problems. So this was also an opportunity to make a API to neatly integrate with gRPC. So let's talk about implementing HTTP2. So some of the goals that we had for this, and some of I came up with when creating this presentation. First of all, we wanted to be compliant to the latest specification. So this is removing a lot of the logic, like in the first place. Wanted to make it fully effect-based right now with AO. So right now you can use it just with AO, but in the future I want to kind of experiment with different effect-based schedulers and with like pure effects in general. We take cstruct over bytes because OCaml big arrays, cstruct are just OCaml big arrays wrappers, and big arrays can be a bit faster than OCaml bytes. And also the previous implementation also used big arrays, just a different wrapper, and also AO uses cstruct all over the place. So so that was pretty nice. I wanted to do modular parsers and serializers. Right now the standard is Armstrong and Faraday. Those are the two standard libraries that you use for parsing and serializing. And I just want to again, experiment with effects and effect-based parsers, for example, which AO includes in some way. And two things are the things I'm going to talk about right now, actually. And to just begin to like, what are those? I want to take a quick crash course from HTTP2. I actually saw a lot of hands that you know what it is, but this is like a one slide. So basically, we have a server, we have a client, we have a one TCP connection. Over this one TCP connection, we have one HTTP2 connection. And what's important, we have several concurrent streams where data floats on both, like bidirectionally. And this is concurrent streams over a single connection, so we have concurrent read and writes. I want to expose to the user like the ability to read and write to those streams concurrently. And just some terminology, request just means opening a stream, and the request body is the data that flows through the stream. And what's important is in HTTP is this is a pretty complex protocol. I mean, there are so many edge cases in HTTP. When you look at the several implementations in other languages, not all are actually fully compliant with the spec because this is a complicated spec. So those two things are pretty important. We want to, because the immutable state, when you design the implementation with an immutable state, it just makes your life easier and makes the life of maintainers easier. And there is less room for race conditions. And also for the functional API, we want to design the API of HTTP2 in such a way that like the data availability is defined by the API and it's safe by design and it's very functional like it should be in a very functional language. So the base idea looks like this. We have some state. This is the very basic idea of the design, how we designed the HTTP2. We have some immutable state. We got some async events. Each of these async events returns some transformation of the state. We take the first that finishes, we take the transformation from the first event that finishes, we get the new state, and we loop back. And we take the transformation, and we don't return the state directly, because when multiple events finish at the same time, we want to bind those transformations. So it kind of looks like this. We got some event, like reading from a network socket, we're waiting for some bytes. We return some transformation of the state, and we close it in some loop. We raise those events with this fiber any, and we combine those. If multiple finishes, then we get the next state, and we loop back. So in HTTP2, it's like one event at the very beginning. We just wait for the network bytes to, we're just waiting for the bytes to arrive from the network. So in the normal scenario, typical for many implementations, it's kind of like a, also I should mention that, well, we want to write and read to those, to several streams that are in this connection. And each read and write modifies the state in some way. So in the normal scenario, you make like an imperative API, which just mutates the state, and the state is mutable. And there is a case that you can like write after closing the writer. So you close the writer in some fiber, you try to write with the writer in some other fiber. And this is obviously not like a very frequent issue, but it would be nice to design an API in OCaml where this is just not possible to write after close. Same thing for reading. It would be nice to implement API where users don't have to think about if the read is scheduled or not and have to reschedule if it's not scheduled. And obviously we can't do anything imperative because we have immutable state, which gives us a lot of benefits while implementing. So what we do instead is we don't give the user any functions. We take the functions from the user. So for writing, we take some writer, which is unit to data, and for the reader, we take data to unit. And here it looks like this. We use this reader function just after reading from the socket. We parse all of the bytes, we pass it to the reader, and we modify the state in some way. And for the writer, we make it a separate async event. So it just acts as a separate event. We get the bytes from the writer, we modify the state. But this is actually pretty bad, and you would discover this pretty quickly if you want to be immutable. Especially on the server side, you probably want to write something based on what you read, and in order to do that here, you would have to make some mutable variable outside of those functions. So basically, to communicate between those functions, you have to make some mutable variable outside, and we want to be immutable. And also, to accumulate any data, to make some sense of accumulated data, you would have to, again, do some mutable variable outside of the reader. So what you do instead, what we did instead, is we changed the writer, so we changed both the functions, but now the writer looks like this, and it takes the arbitrary type, which is defined by the user, and it not only returns the data, but also returns the updated value of this arbitrary type. So for our use case, it can be, for example, like a call stage, which is managed by this single HTTP stream, and user can match on this call stage, and you have and return appropriate data and appropriate new stage or state of the telephone call, for example. So you have this nice declarative way to make decisions in code. And for the reader, it's similar. We have the arbitrary type. We not only take the data as argument, we also get the type. We match on the data. We match on the arbitrary type, which we call the context of the stream, and we return the updated context. But this is also not great if you want to, if you imagine like a simple echo server where you want to respond with whatever you get, which is not that common, I guess, but it would be nice to have a way to just write right after you read, because, like I said, if you have a echo server, you have to read data from the reader, pass it to the context, then read it from the context in the right, and then just return the data in order to make a simple echo server. So that's pretty bad. So instead, we remove the reader immediately, totally, and we make like a general handler, which is also triggered on every read, but instead of just updated context, we return a list of actions, and this type is actually provided by the library. So not only you can update the context, the state of the call, but you can also immediately write some data or close the stream completely. So now you have the call state, you match on data, you match on context, and you return appropriate actions that you want to take. So now this writer on the left becomes more like a generator thing, which is optional and can be used for additionally, for example, proxying data from one source like RTP to gRPC. So this is what we came up with for like a functional style of writing and reading data. But now let's talk about the creation of a new connection itself. So typically what you do, you imperative, like in a mutable state scenario, you create this loop of asynchronous actions, you close it in some fork, and you have a mutable state so you can return some instance of this connection to the user, so the user can then use this thing, this instance to open up a new stream imperatively. But we can do that, we have an immutable state. So what we do instead is we don't run this whole loop at all internally in the implementation. We just give the user the connect function, which gives them like an initial iteration, initial state of the connection. And the user is responsible for running the whole loop. And if there is any possible next state, they can just run this continue function, so it becomes like a pure state-to-state function. And in order to open up a new stream or any other action that we want to take from the connection level, we just inject those variants into the continuation function. And this acts really, oh God, I got 7 minutes. And this acts really nicely if you want to integrate it in gRPC in like a higher, bigger event loop. So this is our event loop, which is smashed it into a nice state-to-state function, this continuation function. And we just use this in a bigger loop in gRPC channel. So for those who don't know, gRPC channel is like a client-side abstraction which manages multiple HTTP connection and multiple streams in those connections. So the user of gRPC doesn't care about HTTP at all. So if you quick crash course from channel, if we got this HTTP connection I showed you earlier, and we got the RPC call. This RPC call is attached to some specific channel that is created by the user, and this channel is managing multiple of those HTTP2 connections, and the job of the channel is to point to the right stream to like open up a new stream and use appropriate stream in appropriate connection. So we take this big event loop of HTTP and we just put it in a bigger event loop of some web framework, or in gRPC in this case, and the state of gRPC channel includes the states of each HTTP2 connections. And this kind of looks like this. This is the part of gRPC channel implementation. So kind of similar what you saw before. We got some events. Some of those events are connection events, which are all of the HTTP2 connections managed by this channel. And then we raise all of those events. We get the transition, with the transformation of the state, and we get the new state. And if there is any, we loop back. And this is all closed in like a recursive function running in a fork. And this kind of how this HTTP2 event looks like in the gRPC channel implementation. So this record there is representing one HTTP2 connection, and this next iter function is what I was talking about. This is exactly this continuation function. So we just treat it as like an async event in a bigger loop, like a gRPC channel. And when it finishes, we just make a state-to-state transition of the whole gRPC channel state. And you end up with something like this. This is the final like maybe final gRPC API of OCaml gRPC. So you make a channel at the top, and you make this handler, which is very similar to the HTTP2 handler, but this is actually better because you don't match on pure bytes, you match on like meaningful messages from the proto file, where types are generated. You match on the arbitrary context type, and you return appropriate actions. And you also have some writers, so for example, we can use it to read data from RTP and send it immediately to the gRPC server. And then you use generated service and RPC. You attach it to the channel, you give it the writer, you give it the handler, and you match on it to see if it's okay. I mean, in both cases, you get the final value of the arbitrary type and error if there is any error. So I definitely got too much time left. I didn't talk about something, but let's just accept that. Both of those libraries are open source. So if you're interested in using it or contributing, just come up to me, say hi. And they're very, very work in progress, but they're used in production for quite some time. And we're also hiring at Dialo. So if you're interested in joining our team or you're an interesting person generally, then just come up to me and say hi. And that's all I got here. Thank you.
Thank you, Adam. Is there any question? We have 10 minutes.
How do you deal with parallelism either like at the like service level with Dialo or like even with like gRPC, right? Like do you just do like domain.map or something, or do you have at the service level, do you have like multiple instances running, or I don't know?
Right now the parallelism is not exactly implemented in the gRPC, so we just at this time we just use like we spawn a domain for, actually we use something called executor pool, which is a thing from IO, which just like manages the fibers in the separate domains. So it manages the parallelism itself, and we just use this for spawning RPCs of gRPC. But yeah, it should be pretty much available to just pass the executor pool or the domain manager, I'm not sure what is it called, to the gRPC channel, for example, for it to make the parallelism available, I think.
What about at like the service level? Like, do you just still have like one program running that handles all calls, or like?
No, not right now, but it was for the most time, and it was my like context when implementing gRPC that it needs to be ready for this kind of environment, if that's what you're asking.
Yeah, cool.
Okay.
Is there any other question? Cool. Thank you, Adam. Great.
Thanks.